yeah, I mean, this is the question I wanted to do anyway. So, all right, we have pulls up. And voila. All right. Now, again, you guys can use Desmos. If you can't figure out what this thing looks like, you might want to use Desmos. It'll definitely help. But even better is if you can kind of figure out what this thing looks like. Now, that's not my first priority, right? My first priority isn't that you can figure out what this thing looks like. So if you want to use Desmos, totally go ahead. But even better is if you can figure it out. And I'll show you when I do it, I'll show you how I would figure it out. 828. I did 828 actually. Jacob, here, let me try and find the video. You work on this, I'll find the video. Yeah, no problem, right? Here, but I'll find the video for you, and then you don't have to, or I'll find where in the video it is. Now you don't have to go digging for it. I did 829 as well, so I did them both. Yeah, I'm pretty sure I did them both. So there's 820. that specific one. And then let me see, where is 29 start? So that's 28. And this is 29. Yeah, I mean, like for A, let me just say for 829A, like do either, you can do integration by parts or you can do substitution. In fact, substitution might not be okay. In fact, I feel like I did do 829A. Yeah, I definitely did do it. Like briefly, right? I kind of like went over it really quickly. So here's 829A. If you want to, in the sense that like, so just basically, are you saying, can we switch X and Y sort of thing? Or do you actually want to solve it for Y equals? Like you could do it definitely both. So like, I think when you look at this, yeah, okay. So when you look at this, probably what you're going to do, okay, yeah, you could solve for Y. There's a bunch of ways you could solve for this. When you graph this thing, so actually I could just graph it because I told you could use Desmos, so you can all sort of plug it in. Where the heck is my pen? There it is. So if you graph this thing, it looks something like what? So it looks like, okay, here's your axis. What? Seriously, pen? Why aren't you working? Sure, Jacob. Actually, we'll kind of do something today. That's like question 4. Actually, this is kind of like question 4. All right, so you should get something that looks like, what is it going to look like? It's going to look like this, right? And you're trying to integrate this. So you could definitely do this in a lot of ways. I mean, I actually have an Apple Pencil. And I have an iPad too. But no, it's just a matter, oh no, I put that in my cup. No, it's just a matter of like what I prefer to use. And this is actually not the Microsoft pen. This is like a cheap knockoff. So I just got to get it replaced. That's what happens when you use the cheap knockoffs. But yeah, so You can do this actually both integrating in X and Y. So I'll maybe talk about how to do it both ways, and we can talk about it. And then Jacob, yeah, I mean, they're all, I love, I mean, it's just such a wonderful thing of technology that we can write on our screens now, right? I do, it's my wife who loves Apple stuff, but listen, okay, I believe not in hating. So let me say, I'll do this both ways when we solve it. I do despise Apple, and I generally despise Microsoft, but I believe that you shouldn't despise things just for what they are, right? Like, I shouldn't hate Apple just because it's Apple. I can recognize that Apple does some things really well, that Microsoft does some things really well. And when they do things well, that you should give them credit for that. I think iPads are phenomenal for like taking notes and writing on screens and things like that. I think they're probably a little bit overpriced, but they're great. And there's no doubt that, you know, it's a quality product. I just think it's maybe more expensive than it should be, right? Microsoft, I think, has made like great product in terms of their like online office suite, like, you know, doing some of their stuff, putting Excel online, very similar to like the Google Office suite with docs and sheets and that sort of stuff. So Microsoft's done a really good job of that. Sure. I don't know if that was like a sort of a historic punch there, Saeem, at some of the things that went on with Jobs and Gates back in the day. So, you know, I think you guys got to give, you know, you should give credit to a good product where credit is due. Like blindly sticking to something or hating something or loving something just because you always have is, I think, a bad idea, right? Things change over time. And you have to be willing to, you know, give credit where credit is due. iPads are really great for writing, period. So yeah, I do have one as an emergency in case this thing explodes. And that's why I have one, because I think they're good. Yeah, and you know, it's things like that. It's also practice. You know, there was a time when I thought like Google was the more upstanding company versus Apple, but over time that has actually changed. Like Apple is now, in my opinion, more upstanding than Google. Like it's weird that over 10 years that sort of shift has happened, but stuff like that has happened as well. Okay, I'm gonna do 30 more seconds because we're almost already at 8 minutes for this question. I'm gonna pour myself some tea while I wait. And like back in the day, everyone, like this might be too young for you guys, I'm not certain, but the original like iPods were awesome. Like they were phenomenal. Like especially the big Aziz, I don't know if you remember, but like the original iPods, like the big fat thick ones, you couldn't break those things, right? Like my wife has hers from like 15 years ago and it still works. Yeah, exactly, with the circular touchpad, just phenomenal. Like those things were just, you know, built to last. And, you know, back then being able to, you know, have 500 songs on your device was crazy, right? That was definitely it. I remember the first MP3 player that I had, and it could hold 12 songs, I think. And that was crazy for us. We were like, oh my God, it could hold 12 songs, right? So but yeah, so I mean, you know, Apple has done some good stuff in their time, and you get, like I said, you got to give them credit where credit is due, right? Okay, so majority of class said C with a little bit of a follow-up in B. B is the right answer. Now, I actually haven't done this question. I can just, you know, I've got the answer sheet in front of me. So you're going to watch me do it live. And let's see what I get. Hopefully I also get B, otherwise that'll be embarrassing. So again, first thing is you got to figure out what this looks like. Now, again, for us online, it's totally free if you use Desmos. We used to emphasize a little bit more in the past when we were in person about being able to figure out what these things look like. Just because, you know, if you were in person and I asked you this question, you don't have Desmos. So the way that I figure this out, everyone, is I know, just me, you know, through experience, and maybe you do as well, is that the graph y equals x to the 2/3 looks like this, you know, kind of looks like, you know, how you draw a seagull, you know, when you were a kid. So it looks like how you draw a seagull. So when I look at the equation, x cubed is equal to y minus 1 squared, I'm going to solve that for x. And that's going to give me y minus 1 to the 2/3. Okay, so I know that that's basically, if it was just x is equal to y to the 2/3, that would look like this. Or maybe let me label my axes. I used to give students a lot of hell if they didn't label their axes. I was a jerk as a TA. Okay, so this will look like this, right? This is what x equals y to the 2/3 looks like. But then because I've got y, yeah, sure, that's fine. I probably do draw them the exact same way. My flowers and suns are the same as I drew them when I was like 8 years old, right? And which is to say it's all terrible. You've seen my drawings, right? They're not good. Okay, so this would be x is equal to y to the 2/3, but it's y minus 1, right? So that means that it's a shift up 1 unit. And the way you can see that is that when y is equal to 1, x should be equal to 0, right? So when you shift it up a unit, it should be 0, i.e. that's that like cusp thing there, right? So this is what this would look like. Okay, so that's kind of how I figure out how what this graph looks like. And then we're looking also at the line x equals 1. So if we draw x equals 1, it might look something like that. And this is the area that we're after, right? So I drew that before, but this is kind of like, this is how I would figure out what this graph looked like if I didn't have access to Desmos or something like that. Okay, so there's a couple of ways that we can solve this now. I think that the easiest way to solve this is going to be to integrate in the y direction. And what I mean by this is basically turn your head to the side. This is gonna, like, I can only do this so much, right? But you're gonna turn your head to the side and you're gonna look at this function and like, because this isn't a function, right? Like the way this is drawn right now, it fails the vertical line test. That's no good. There's like a bunch of different curves going on. What a mess. But if I turn my head to the side, right, it looks kind of like, it looks kind of like this thing. My axes are kind of weird, right? Because the positive axis is to the left, but it looks like that. And I'm like, oh, I can integrate that, right? Like that's, if I given you that curve to begin with, you all, I think, probably could have done that. So if I integrate in the y direction, it looks sort of like this. And so what we need to do is figure out what these points are, right? So where does the line x equals 1 pass through my curve? So let's do that first. So let's find where x equals 1 intersects x cubed is equal to y minus 1 squared. And for that, right, we're going to just substitute x equals 1 into the equation and to the right. So we'll get y is equal to y minus 1 squared. So that means that plus or minus 1 is equal to y minus 1. Okay, so if it's plus 1, or okay, so that tells me that what, y is 0 and 2, I think. Yeah, that looks right. Okay, so I didn't draw my picture perfectly, but basically it meets at 0 and it meets at 2. So now I'm going to, again, looking at it from the side, right? I'm going to subtract the green function from the blue function. The green function is the bigger of the two functions. So I'm going to subtract the green function from the blue function. So the area is the integral from 0 to 2 of the green function minus the blue function. Now I've solved for the blue function right here. So minus y minus 1 to the 2/3 dy, right? And we can solve that, or you could do like twice the integral from 0 to 1, or twice the integral from 1 to 2 if you really wanted to do it. All of those are totally good. So what am I going to get here? So I'm going to get y minus, so it's actually going to be plus y minus 1. No, it's not. It's still going to be a minus. Y minus 1 to the 2/3. So if I add 1 to that, I get what, 5/3? So this is going to be 3/5. Y to the 5/3, 0 to 2. Let me just double check that quick. Yeah, that looks good. When I plug in 0, well, let's plug in 2 first. So I'm going to get 2 minus 3/5 times 1 to the 5/3 minus 0 minus 3/5 negative 1 to the 5/3, right? And hopefully I get the right answer here. So I'm going to get 2 minus 3/5, which is what, 7/5, I think. And then I'm going to get minus negative, oh, there's so many minus signs. So the cubed root of -1 is -1. If I raise it to the 5, it's still -1. So that's negative, negative, negative. So it's just minus 3/5. So that should be 4/5. Was that answer B? Woo! Right? But again, like 80% of the marks is just getting to that point. And then after that, there's like 2 marks for actually doing the integral. But at that point, you can go plug the integral into Wolfram alpha. Why is it 1 and with the 2/3? So like, are you asking, say I'm just about like this? Okay, so what I want you to do is look at this thing. Oop, that's a weird thing. So maybe let me like redraw this now, where again, we've sort of like tilted our head, right? So here's the x-axis, here's the y-axis, and then here's y minus 1 to the 2/3, and then here's the equation. Ooh, that's not straight. Here's the equation x equals 1, right? So remember when I'm finding area, I subtract the bigger function from the smaller function, right? And so the bigger function here is x equals 1, right? That's this part here. And then the lower function is the y minus 1 to the 2/3. That's the blue thing here, right? And I had solved for that earlier, right? Where did I solve for it? Right here, when I was trying to figure out what the graph of the thing looked like, right? The integral of the green function is 2. Yeah, that should be true. Yeah, as a rectangle, absolutely. Yeah, its integral should be 2. And then, yeah, if you want, you could just subtract the integral of the blue function that way if you want to do it like that. And in fact, you can see that it's 2 because it's kind of like this part minus this part. Like that's the part of the green function that comes in. So you can see that the area is 2 there. Where does the 1 come from? Like this one? Or is there another one? Yeah, exactly. Yeah, that's the curve x equals 1. Yeah. So is everyone okay? Now this is a little weird, right? Like we're not used to looking at these graphs from the side and integrating them in that direction, but you totally can. And the trick is now, instead of writing all your functions as y equals something in terms of x, if you want to integrate in the other direction, that's fine. But now you have to write everything as x equals something in terms of y, right? So you rewrite your expression in terms of y and you integrate that thing. And you can totally do that. There's nothing wrong with that whatsoever. Now, there's another way of doing this, which you might say, well, maybe I don't want to do that. Maybe I just want to integrate, in the x direction. Okay, and this is sort of like numeracy number 4. Okay, so this is sort of like a nice thing that we can do here. If you're trying to think about like how to do the numeracy problem. So let me maybe redraw this, and let me draw this better this time. So let's draw x equals 1 first. So here's x equals 1. And let's label our axes. And then we're going to get something like that. Okay, so here's 0, and here's like 2 up here, like so. Okay, so we're looking for this area here. So what I want to do is I want to figure out, okay, instead of thinking of the blue curve now as a single curve, because it's not a function, right? Because it fails the vertical line test, why don't I sort of split it up and let's think about the top curve as being one thing and the blue curve as being another. And Terrace, I think this is like sort of what you were talking about in terms of solving for y, right? So what I'm going to do is I'm going to take my original equation, x cubed is equal to y minus 1 squared. And now I'm trying to figure out like what these functions are as equations of y. Okay, so I'm going to try and solve this equation for y now. So if I do that, I'm going to take the square root of both sides. So I'm going to get plus or minus the square root of x cubed is equal to y minus 1. So that implies y is equal to 1 plus or minus the square root of x cubed, right? Or maybe let's just write that as x to the 3/2. Might be a little bit nicer, right? And we can probably guess, it looks like I'm going to guess that this is 1 plus x to the 3/2, and that the blue curve is 1 minus x to the 3/2. Okay, and so now we could do our integral as the integral from 0 to 1 of the red curve. No, that's green. That is not red. 1 plus x to the 3/2 minus the green curve. Right? Like so. Okay, and now the ones are going to cancel each other out. All right, so 1 minus 1. So then I'm going to get x to the 3/2 minus negative x to the 3/2. So this is going to be 2x to the 3/2 dx. So what is that? So that's going to be 4/5 x to the 5/2 evaluated from 0 to 1. And that's 4/5, same answer, right? Which we expect, right? You should get the same answer. And then from a numeracy standpoint, this space would be the set of x, y, such that, and then 1 minus x to the 3/2 is less than or equal to y. It's less than or equal to 1 plus x to the 3/2, like that, right? So in terms of the numeracy thing, which I was sort of asked about, what you're trying to do is say, is my space bounded above and below by two curves? And in this case, it is, right? One of those curves is the bottom curve is 1 minus x to the 3/2. And the top curve is 1 plus x to the 3/2. So when you write your set like this for the next assignment, this is the fourth numeracy question. Like this is how you would write it, right? So this is, you figure out what those curves are and you use that to fill in your information. Okay, so any questions about that? Oh, you're right. That should be in blue. Absolutely. Let me fix that. Boom, like that. There we go. And write that. That's one. But you're right. Yeah, absolutely should be one. When I write it like this. Okay, so here's basically what you're going to do in order to figure this out. Here's the little trick I use. So what you're looking for when you write this thing out is what's the smallest x value and what's the biggest x value. Now, in this case, it's not too hard to see because our shape doesn't do anything too weird, right? The smallest possible x value for my area here is 0, right? Do you agree? And the biggest one is x is equal to 1. So that part's okay. Okay, now what you're going to do, okay, is I want you to just choose an arbitrary point x. Right, so it's an arbitrary point x. And what I want you to do is walk in the direction of positive y. Okay. And what I want you to do is when you enter the area, right? So you notice that this is the place where I actually enter my area. Keep track of what that curve is. That's your bottom curve, right? And then you keep walking, you're in the area while you're in here. And then boom, when you leave the area, keep track of what function that is. And that's your upper bound. Right? So you take a walk along the positive x or positive y direction. When you enter your space, that's your lower curve. And when you leave your space, that's your upper curve. And that's how you determine what those bounds are. Right? So it's saying these are the collection of all points, x and y, but not just any x and y. X has to be between 0 and 1. Okay, that's fine. We've guaranteed that. And then if you give me a specific x, it also has restrictions on, for a given x, there are restrictions on what the y value can be. And the y value has to be between the blue thing and the red thing, the solid blue bottom curve and the solid red upper curve. And that's sort of you specifying what this space looks like. That would be the y value. So in fact, if you want to switch this around and you want to write this as a type 2 region, so you'd say y is between 0 and 2, right? And then you sort of pick an arbitrary y. This one's actually a little bit well, it's not, no, it's not that bad. And then you say, oh, look, I entered the curve on the blue thing and I left on the green thing. So now it's going to be, what was this equation again? Y minus 1 to the 3 halves less than equal to x less than equal to 1. So that saying that 0 to 2 restriction you would use if you were doing it in the other direction. So both of these describe the same set, but they sort of describe them in different directions. Yeah, exactly. Yeah, this thing here, let me see if I can fill it in with my highlighter, like specifically this thing.
The exponent is 2/3, not 3/2 at the bottom for y.
Okay, awesome, thank you. 2/3. Okay, so that kind of gives you a nice little thing there. So does this help for numeracy 4? Everyone, do you kind of like see how to do that? You're just saying, what's the curve that you like, where you enter, and then what's the curve where you leave, and that sort of thing. And again, this 1 here comes because we're talking about the curve x equals 1. Okay, any other questions? Everyone's good? All right, let's try something else. Oops. All right, I want to go straight to this one here. I think it's been a long time since we did the last question. Oops, not share, relaunch.
I like the previous question. I like when we like, it kind of forces them to flip the axes. I feel like that's very good in terms of show understanding as well.
Yeah. And I mean, I guess another thing you could do as well is like, if you didn't like looking at it on its side, you could actually literally flip x and y and say, listen, what we name the variables doesn't actually matter, right? Like who cares what's called x and what's called y? So let's actually flip the variables. And then you can actually graph that thing in the XY plane and solve it that way. So that is another thing. It's a little bit more roundabout. Like I wouldn't necessarily do that, but you could.
I guess so. I mean, like we define x and y however we want, so we could theoretically just flip them again.
Yeah, or in fact, if you wanted to, just like call the y-axis the horizontal axis, right? And then the x-axis the vertical axis. Like it's all just, the fact that the y-axis is the vertical axis is just convention. And there's nothing saying you can't break convention.
I feel like the problem with that is just sometimes like you're going to confuse yourself just because of the norm you've been practicing pretty much your whole mathematical career. You practice how to do it one way, and now just flipping it, I feel like inherently it makes more mistakes along the way, especially like calculation errors and stuff.
Yeah, but it's one of those things. It's like same thing with implicit differentiation. Sometimes we differentiate with respect to y. Like sometimes you have to break that mold in your brain, right? Like say like, okay, I recognize that these are, this is just a convention, that I don't have to do it this way, and that can be beneficial sometimes.
Definitely agree.
This is a really fun question too. I really like this. Right?
Yeah.
Yeah.
I think it's one of these, if you actually understand what's happening, you can solve it. But if you don't, you're just kind of staring at this, not knowing how to proceed.
Yeah, this is totally a question. Exactly. Like if you just don't know what you're doing, you're not going to have a chance here.
No.
Something that inverses the function by the x-axis. So yeah, what do I want to say here? So the inverse is the reflection of the original function about the y equals x-axis, Connie. So I think that's what you're thinking of, right? like the graph of the inverse is the reflection of the original graph about the y equals x-axis. Now, that's a rough way of doing this question. You might be able to do it. Yes, yeah, that's what f inverse of x is. Yeah.
Correct me if I'm wrong, was this question once on a previous test multiple choice back in the day? I don't know why this question is really familiar in my head, and I'm not sure where it's.
It might have been. It might have been. I feel like maybe it was a test, or it might have been like a quick assignment question, something like that. It was on something.
I don't know. I remember it being like, remember back then we used to have multiple choice on the tests back in the day. I don't know why I remember it either being either the multiple choice or the short answer section where we had like that small box where you put your answer at the bottom. I think it was, I don't know why I remember it from that period. I might be wrong. It's been a while.
Yeah, I'm just trying to think, like, this is a hard enough question that I'm not certain I would have given it, but maybe I did. Maybe I was just feeling angry at the students and was like, I'm gonna torch you all or something. Well, I'm not doing that now though, right? So there's no reason to be sad. So my logic here. So getting the inverse of so Brandon, you could try that with an actual function, right? So try it with the function x cubed. So x cubed is strictly increasing, and everyone, you could try this as well, right? So x cubed is strictly increasing, and on the interval 0, 1, its range is 0, 1. But what is the integral of x cubed versus what is the integral of the cubed root, right? And are they going to be different?
Mm-hmm.
The two limit questions, yeah, I don't know. I don't think we're gonna have two limit questions. It's appealing. I pitched it to nobody and have decided against it. So
I don't know why you'd have two limit questions. That seems very repetitive.
maybe they all really love limit questions, I guess. I mean, we've really trained you all for that. Like, here's a graph, and what's the limit as you approach the left. So I think you're all very trained on that now.
I think so. Some people coming to the tutorial and answering limit questions on the spot before I even ask them at this point. So
yeah,
I'm very comfortable with it.
I mean, that's good. I really like that. You guys will be fine. What's the worst that could happen?
I do believe you guys will be fine, actually. On a side note.
That being said, every now and then an instructor is just like, their term tests are one way all term, and then their final exam is just completely different. You're like, what the heck just happened? So, Dad, you mean as long as you pass with the 63, you're happy?
That's true. There's two levels of passing. You can pass the course, but not achieve the minimum for the commerce/management requirement. So,
but I think for you all, 63 is the pass, right? Like, that's what you all think is the pass. It's not, right? Yeah, we don't know yet. 6, 8, something like that.
6, 7, 8, 12, 15.
Yeah, but what does it matter if there's 6 questions and each of them has 10 parts?
I mean, the exam has not been written yet, so there's no real definitive answer anytime soon. I was worried more about the assignments and tests more than the exam at this point.
Not that there is much left. But no, we have 100%. It has happened where students have been doing great all year, and then just for whatever reason, the final exam hits and their brain shuts down, right? And a student will go from doing really well all year, getting 80, 90 all year, and then just get crushed on the final 30, 40. And not even because of the final being weird, just because, something happened, right? And their brain just didn't quite work, or maybe they had a bunch of exams coming up or whatever. Stuff happens.
203, 67%. Yeah.
Yeah. It doesn't, and so saying, what do you mean about what's going on with next week's material? Like, do you have a specific sort of thing there? And then, you know what, it doesn't matter, everyone, you just try your best, right? Because I mean, like, there, no one can ask you to do any more than that, right? Yeah,
Mhm.
next week. Yeah, next week is oh, I see. No, next week's no, you know this. Come on, we've had 6 tests now, right? Like next week's test will stop today.
You know what's funny? I get at least, no exaggeration, like just the week of the test, I get at least 10 or 15 emails regarding that same question. It- like, and it's sometimes it's funny because it's the same person that asked me on test 5, 4, and 3, as if it's gonna change on test 6 all of a sudden.
Yeah, always the same. Always the same. That's too bad. Hopefully it's not too bad. Now, we have a 24-hour exam though, right? So you have some flexibility there. Okay, so this is interesting distribution here. The correct answer, everyone, is C. C is the correct answer. And some of you might have guessed a function that works and then just found the inverse and tried it. But so for example, like x squared would work, right? And if you actually plug in x squared and you compute the integral, you get 0, 1, and then you could try computing the square root of x, you would get the right answer. But that being said, if I asked you this is like a long answer question, you'd have to do a better justification than just saying, hey, x squared happens to work, because there could be other functions that give you the answer 1/3. So the way to see this is basically sort of just like do a generic function. So we're just going to draw a nice big graph. Okay, here's our x-axis, here's our y-axis. Here's 1 and here's 1. Okay, and you're told the function is continuous, it's strictly increasing, and its range is all of 0, 1. Okay, so basically what that means, draw whatever function you want, it doesn't matter. I know, strictly increasing, so it has to look something like that. Okay, and you're told this thing right here, right? This is the integral from 0 to 1, f of x dx. You're told that this is 1/3. Okay. Now, the question says, what is the integral from 0 to 1 f inverse of y dy, right? So notice again, this time we're integrating the same function, but in the y direction. And it turns out if you do that, if you view the blue function by turning your head to the side, that is the inverse function. And so what I'm asking you for is, what is this area? All right, so the answer is the green area. Okay. Okay, so what about, can you be more specific, Lee, about like what about that like, is it the fact that if you turn your head to the side, that's the inverse function? Yeah, okay, sure. Here, so let's play around with a couple of examples, okay? So here is, well, here, let's be consistent in our color scheme. So we've got x, y, all right? And now here, let's say this is the curve y is equal to x squared. Now, if I were to solve, right? So if I want to view this from the side, right? Like turn my head to the side, what I'm trying to do is to write it as a function of x instead, right? So instead of being y is equal to x squared, I'm trying to say x is equal to something. And if I do that, right, if I solve for x, I get the square root of y. Do you agree? Notice that that's the inverse function to x squared. And generally, right, whatever this function is, it's y is equal to f of x. When you try and solve that thing for x, what do you get? Well, you kind of put the f on the other side, but when you do that, you have to put the inverse over there. Yeah, exactly. Yeah. right? Like that's how you would solve for the other variable, right? Is you would apply the inverse function to both sides, and then f inverse compose f cancels itself out, right? So when you actually take this equation and solve it for x, you get f inverse of y out. Does that make sense? Okay, cool. So what that means is that this green area here is the integral of the inverse function. And why do I know then that it's 2/3? Whatever it is, it has to be 2/3. Like what happens if you add up the green and the blue? What do you get? Right, exactly. It's 1 minus a third, i.e., yeah, exactly, Jeremiah, right? So the total area is it's a 1 by 1 square, right? It's a width of 1, it's got a height of 1. So the total area of this rectangle, so the total area of the rectangle is 1. And the blue area is 1/3. Maybe let me say that. The blue area is 1/3. So that must mean the green area is everything left, right? So the green area is 2/3. Yeah, it's not too bad, right? It's just sort of like cleverly understanding what the relationship between the function and its inverse, and when you integrate it in one direction versus integrating it in another direction, it's surprisingly not too hard, right? But it gives you this sort of like nice intuition behind how you're supposed to attack this problem. Yeah, the diagram definitely does give it away. Yeah, absolutely. So I think that's a nice little problem, right? It turns out to be surprisingly not too bad. Like the question looks bad, and then you draw the diagram, you're like, oh, it's not too bad. Yeah. Okay. So I think those are the only two we're going to get done today because the class ends in like 6 minutes. So we can stop though, and we can just break out into office hours now if anyone wants to. So I've got a couple questions. 828. Somebody asked for, I think 829A, but again, I did do it, so I linked to that. Sure. So can you be more specific, Simon? Like what part of the inverse? Like why do you get it's the inverse curve? Sure. Okay. So you agree that the blue curve is y is equal to f of x, right? And what that means is that every point on this curve, this is the relationship between x and y, right? So right now it's just kind of like it is a set of 2 points, x and y, but we're told explicitly the relationship is that if I give you an x, the way that you compute the height is by computing f of x, right? Now, what we're going to do is when I want to integrate along the y-axis, right? When I want to compute the green area, you're trying to do the other thing, right? You're trying to say, if you give me an arbitrary point y, how do I compute this length right here, right? So if you're given a point y, that's now the x distance. So given y, what's the x distance? So here's the equation which relates x and y. And if I want to figure out how to get x in terms of y from this, what I'm going to do is I'm going to apply f inverse to both sides. And then f inverse f cancels out, and I just get x, right? How do we know that the graph looks like this? So yeah, what do I want to say there? So I mean, certainly, so the curve, first of all, the curve that okay, great. So the curve that I drew was arbitrary. Now the question asks us to find this thing right here, right? And I know that this is the same curve, right? Because if you just y equals f of x and x equals f inverse y, these are the same, right? There's like the relationship between x and y here hasn't changed. So when I give you the graph, the blue curve, even though like it doesn't matter how I've chosen to write it, the relationship between these two variables hasn't fundamentally made a difference, right? Like if y is equal to x squared, then the fact that 2, 4 lies on this graph doesn't, like, it doesn't matter if I say that this number is the square of that one, or if I say this number is the square root of 4. Do you know what I mean? Like 2 is the square root of 4 and 4 is equal to 2 squared. Okay, whatever. It doesn't matter how I've chosen to write that relationship. The number is still 2 comma 4. I think that, like, hopefully that kind of made sense. Like, do you see what I'm saying? Like the relationship between X and Y is the same. So when I write F inverse Y, like I haven't really changed anything. And then when I say integrate F inverse though, I'm saying kind of like turn your head to the side, because that's how you see what the inverse function is you turn your head to the side like that. So hopefully that makes a little bit of sense. So let's see. People are asking about numeracy 2 and then 828A and then 29A. Okay. And then 28A and then 29A. Okay, so here, let me go get the graphs of these things, because I think they're here, right? So I can just take them from this instead of having to go get them again. So, all right, here's 28. I don't have the tutorial question, so I can't help with that. And then 9-2B. Okay, so let me just pull up what specifically. Okay, so 20, right? A says just find the integral between what? Oh, -2 and 0. F of x minus g of x dx, right? So between -2 and 0, that's this area. And then this area here. Do you agree? Everyone agree? So this thing is the blue area. Okay, but here's the thing. So actually here, let's ignore that area for now. Okay, so here's a red area and a green area. Do we agree these areas are the same size? Okay, however, they are negative signs of one another. Do we agree on that? Is everyone okay with that? Well, then maybe the textbook is just like moved the answer or not. But like here, they are the same size and they're different signs. And so they cancel each other out, right? The sum of these two things is 0. And so we don't have to worry about them. It's not, there's not increasing and decreasing here because there's two functions, right? So here on this thing right here, right? So on this interval, we have what? G is bigger than F, right? But on this interval, they switch, right? And F is bigger than G here. And so because we're just looking at the integral of F minus G, on the left-hand side, they're negative, and on the right-hand side, they're positive, right? Because we're looking at the difference. We're taking F and we're subtracting G. So if F is bigger than G, the area is positive. If F is less than G, the area is going to be negative. So here our area is negative, right? We've got a bunch of negatives. Here our area is positive. But they're the same in absolute, like they're the same in absolute area, but they have different signs. So they cancel each other out to give 0. Is that okay? Does everyone sees that? Okay, so then what's left? So those two cancel each other out, right? So the only thing left, so what part is bugging you? Do you see that it's this rectangle? Is the area, right? Because we've got F here, we've got G here. And so if I integrate their difference, right, it's just the area between them. This is a rectangle with length 1 and with height 2, right? So the area between the graph between -1 and 0 is the area of this rectangle of width 1 and height 2. Right? Or equivalently, you know what the equations, yeah, exactly. And if you really want to do it as an integral, it's the integral from -1 to 0. The top function is 1. The bottom function is -1. Equals, did I subtract correctly?
You did.
Yep. Yep. Right. Yeah, exactly. Right. Because that's the formula for the equation of a rectangle. So, and we know the definition of the integral, remember the definition of the integral for us at least, is the area under the graph. And so in our case, though, this would be the area between the two functions. Christian, correct. Yeah, exactly. Okay, everyone's okay with that? This is answer 28A. Everyone's okay? So signed area doesn't, no, it totally matters, Davin, right? Because that's how we canceled out these areas. Right? So it is signed, but we don't care. What we don't care is about which is above 0 and which is below 0, because you see that we've got like the extra minus sign here kind of takes care of that. So it's true, this area here is like -1, right? But when you look at the integral, so the integral is the integral of f minus g. So the area of g here is -1, and I get -1. You see what I'm saying here? Like the minus signs work out to give you the right sign anyway. So that kind of goes over that way. The beginning part of 9, but with 28A. I mean, the beginning of, wait, Jacob, what do you mean part 9? The left f of x part. Can you do the beginning? Part 9, but with 828. I just don't like, yeah, what do you mean by part 9? I'm just not understanding, yeah, what you're asking. What is part 9? Now my diagram is very busy, so let me just clean it up a bit. Oh, 829A, sure. No, I'd prefer not to, because 829 is built to specifically use that graph to make life easier. Like, first of all, we can't do 29A because the integral is from 2 to 3. And for this graph, there is nothing, we don't even know what the function is from 2 to 3, right? So I physically can't. But I am going to do 29 because enough people have asked for it. So let me go get the thing. But yeah, I just physically can't do that problem, right? Because the functions have different domains, so I can't. I just can't translate that problem. I could do something similar, but again, this problem is sort of designed to be doable because of the way the function is defined. Okay, so there's a couple of things you could do. Again, you could either solve, so for 829A, you could do parts or substitution. All right, see these. You could do substitution or parts. I'm pretty sure both give you the right answer. So you're asked for the integral from 2 to 3 f of x, little f of x dx. Okay, so if you do substitution, so let's see, we would let u be capital F, du is f of x dx. So this now becomes, okay, what is u of 2? So that's f of 2. And f of 2 is 1, 2, 3 is 4. And then u of 3 is f of 3, which is 7. I think, right? 1, 2, 3, 4, 5, 6, 7. Yeah, it looks right. Unless the integral starts somewhere else. No, it starts at 0. So it's going to be the integral from 4 to 7 of u du, which is then 1/2 u squared, u squared from 4 to 7, which is 1/2 49 minus 16. Sure, so what is f of 2, right? So the definition, f of x is the integral from 0 to x, f of t dt. So f of 2 is the integral from 0 to 2, f of t dt. We look at the graph. Here's 2. So f of 2 is this area. And I just counted the number of squares. Right? So I've got 1 square, 2 squares, 3 square, or yeah, maybe like 1 square, and then a half square and a half square. And so that's 4 squares total. Is that a good huh? Or is that a confused huh? Okay, what is this area? Like, and if you want, compute it. Like, you know what, you could compute what the equation of this line is if you really wanted to. No. Or you mean like theoretically, could I? Like, because we don't know what f is, right? I mean, we could compute what f is, right? The equation for f on this is what? Y is equal to x plus 1. And so the integral, so f of 2 is the integral from 0 to 2 x plus 1 dx, which is 1/2 x squared plus x from 0 to 2, which is 1/2 4 plus 2, which is 4. I mean, it depends, Natalia. Like in this case, there isn't necessarily a cancellation, right? Like I'm not looking for a cancellation here. It's just like, do you understand what capital F is, what little f is, these sorts of things. Right, yeah, Christian, that's exactly where it comes from. No, we don't have to find the antiderivative of f. Remember, Chen, right? Like the original definition of the integral. Remember, like when we first started doing integration, those pull questions that we did, we'd give you something like this, and we would say, find, the integral from 0 to blah of this function. And the fundamental theorem of calculus came later, right? The FTC allowed us to find an antiderivative and to solve these questions using an antiderivative, but the definition of the integral is just the area under the curve, right? So the only thing you have to do to find, like if you're given straight lines and triangles and rectangles and stuff, you can compute the areas just by finding the area, right? Like you don't, right? Why look at f of x? Because we're saying find the area under, right? What does this mean? This is the area under f on the interval 0, 2, right? Like that's what that sign means. So I'm going to come over to my graph, look at f between 0 and 2, and find this area. Okay, cool. And then same thing, right? The reason why f of 3 is 7 is because here's 3 more squares. So I just, threw them in. So you can do it this way. I'm pretty sure I subtracted the area of the rectangle and the triangle. Yeah, sure. I mean, like, yeah, did you get the right answer? I mean, there's a bunch of things you could have done, right? So I assume you're saying like you took this big rectangle and then you subtracted this triangle. Like that's totally fine, right? Like it doesn't make a difference to how you do it. The f of t dt is a common function for the area. What do you mean, Jeremiah? I'm not quite certain what you mean by that. I mean, it's given to you in the question. Yeah, the question says this is the definition of f. Yeah. Okay, and now everyone, you could have integrated it by parts as well. So I would let u be f of x then, or sorry, capital F. Would I? No, I wouldn't do this by parts. You probably could, but I don't think it's going to lead anywhere very well. So I would leave it like this, and here's your answer. Do you add those squares? Which squares? In computing what? F of 2? Yeah, you add everything up, right? Because you're looking for the area. So you're asking, what is this area? If you want, it's a rectangle of length 2 by 1, and then a triangle of length, right? What's the area of a triangle? 1/2 times base times height. So you can do it like that too. Right, but it doesn't matter how you do it. You get the same answer either way. Jack, sure, let me add you to the list because there's lots of stuff here. Do you just want like any by parts question though, or specifically like one of these graph ones? No, I'm sure I can get to it. It's just like, what sort of thing do you want? Just anything? Okay. Okay, sure. All right, so let's see. So this covers 29A. The next one up, I think, was numeracy 2-4. A bunch of people are asking about. So let me just pull that. And Jacob, too, if you watch that video, I did talk about the homogeneous stuff. So I think it's right at the end. It's the very last thing that we did. So if you're like, oh man, I just want him to get to 11-6, maybe go watch that video as well. And if it clarifies things, great. And if not, I think I should be able to get to it. Like it's only 6:15, right? We got plenty of time. So numeracy 2, can we do 9-6? Well, let me see. There's a couple question 9 parts in here. So 9-4. Oh yeah. The key to 9-4 is being clever. Like you need a substitution, right? So without like saying too much, because it is an assignment question. So anytime you do this, you're going to do this, right? You plug in tx and ty. So we get the integral from 0. So I'm not doing anything here. I'm sure you can all do this part. S squared plus t squared, x squared plus t squared, y squared, right? So you get to this thing, ds. Here, maybe let me write this a little bit bigger, because right now, so e s squared over s squared plus t squared, x squared plus t squared, y squared, ds, right? So what you need to do is think of a nice substitution. No, this isn't 9-4. This is the numeracy -4. Yeah, numeracy 2, question 4. right? So can anyone think of a substitution? Like don't give anything away, but just like what substitution would you use? I mean, you don't want to do the whole thing. I mean, T is just some variable you throw in, right? Because you're trying to measure homogeneity. So it's just like you just throw it in. Denominator could work. Yeah, let me see if I can. Okay, let me see if I can give you maybe some better hint. No, e to the x squared is impossible, but that doesn't mean this one is. Yeah, it is an ugly one. We wanted to give you at least one that really hurt. Long, you can't quite do that, right? Like you can't show it for particular numbers. Like you actually have to kind of show it in general. So what I'd recommend that you do at this point is the following. So you've got this sort of gross thing. And what I'd suggest that you do is you multiply by 1 over t squared, 1 over t squared. So this now gives you s over t squared divided by s over t squared plus x squared plus y squared. Oh, okay, sure. Yeah. Yeah, that's true. That might help. Okay, do you see what to do now? Because remember, you're trying to relate it to f of xy, right? So this kind of looks like what did we start with? So we started with s squared over s squared plus x squared plus y squared, right? And this is what we have now. And we sort of want to relate it back to here. So what should your substitution be? Like, how do you make it look like that first thing? Yeah, Brandon, exactly. That's not a substitution though, Namir. Yes, so far. Abdirasak, yep, that's maybe not the squared. Maybe don't put don't use the squared term. Okay, but otherwise it looks good. Christian, yes, that looks good. Don't call it S though, right? Call it something else. Long, not quite. Like basically what you're trying to do is get this thing to look like this thing, maybe with a different variable name, but you're trying to make it look like that, right? And then you're trying to make this thing look like this thing. It might have a different name, but that's okay. What is du? So this is a function, like t is a constant, right? In this expression, s is the variable you're integrating with respect to. So t is just a number. So you don't differentiate with respect to t, you differentiate with respect to s. Not the denominator same, right? Like, do you guys see it? Like because I'm trying to relate it back to the original function, I want this thing to look like this thing. So that sort of really suggests what the substitution should be. Shanayu, yeah, exactly. That's a great choice. No, but there is still a constant in your substitution, right? Like if you let your Agam, yeah, great. Not quite the whole numerator same, not quite. Oh, and close. Very close. Like again, I want you to turn this, like maybe instead of calling it s squared, now let's call this u squared like this. Like what should u be in this expression? Davin, when I multiplied top and bottom by 1 over t squared, but I don't know if you mean like something else. Abdir's like, that's true. Like substituting it doesn't mean it's homogeneous, but if the point is that when you do the substitution, you should hopefully get back to something which looks like the original function, which would allow you to like relate it to, hopefully make it something homogeneous, but it's no guarantee, right? Like there's no guarantee that this thing is homogeneous. I mean, you don't have to integrate it. You're just trying to get it back. Everyone, you're trying to get it back, right? Like remember when we were doing this yesterday? So we had f of xy equals xy. And when I plugged t into this, what did I get? I got t squared xy. And then I said, oh, look, that's that thing, right? So that's t squared f of xy. So what you're trying to get is that your original function shows up again, right? Like you're trying to like pull out all the t's and then get your original function to show up. No, Brandon, it shouldn't just be dx. Like Brandon, choose a number for t. Like what if t is 7? And use your substitution. What do you get? Right? You don't get du is equal to dx. You get, it's close, but it's not quite that. So Shana, do you know what I'm saying? Like you don't integrate. You're just trying to get back the function, which is your integral. Yeah, exactly, Brandon. Yeah. You shouldn't need to do any integration for this question. Like you shouldn't need to explicitly integrate. You're going to have to do a substitution and stuff, but there is no explicit integration. Like you're not going to get, like the integral sign should stick around. Yeah, it does. But Brandon, that's what you want. You want to get back to where you started, right? But maybe with some extra t's hanging around, because that's exactly what you're doing when you're proving homogeneity, right? You're trying to show if you plug tx and ty in, you get some t's hang, like you can basically pull the t's out, and then what you're left over with is what you started with. If you hadn't plugged any t's in. Davin, yes, spiritually. Now, the important part to remember here is that S here is just a variable name, right? Like we could have called it anything. I could have called this a Z, and this is the same function, right? Like changing it from an S to a Z doesn't make any difference, right? Or if it's a U, it's the same function, right? Because this is, that variable is just a dummy variable. So when you say that, right, keep in mind those S's are different technically, but you've substituted it back to where it started, sort of thing, if that makes sense. Kelly, I'm not quite sure what you're doing there. I don't know why you took the 1 over t's out. So Shana, okay. So again, here, let's do this question here. Okay, so let's say I'm doing xy squared plus x squared y. Okay, so I'm trying to show everyone. Okay, hold on a second. Okay, let's understand what we're trying to do. I'm trying to show that this function is homogeneous, and I don't know what to do. So what I'm going to do is I'm going to plug in t and x, right? So when I do that, I'm going to get tx ty squared plus tx squared ty, right? I haven't done anything crazy. Now, to show that this function is homogeneous, what I need to be able to do is pull out all of the t's and have the thing left over look like the original function with no t's in it, right? Exactly. You take out the t's, you just get back f of xy. When I do this, so I get t cubed x y squared plus t cubed x squared y, which is t cubed xy squared plus x squared y. I've now returned back to f of xy without any t's in it, right? This is your goal. This is what you're trying to do when you show that something is homogeneous. So what we have up here is we started with this expression. This is our expression where we've plugged the t's in, right? So we've plugged the t's in. Now, a lot of you seem to be confused, like, well, why am I trying to make this look like this? Well, I'm trying to get back to my original function, right? I'm trying to get rid of all the t's and just get back out something that has my original expression in it. And so that's why, that's why I'm doing that, right? That's why I'm substituting that away so that I get something that looks like the original function again. So for all of numeracy 2, we're just trying to show how it's homogeneous. Well, you don't know all of them are homogeneous. Some of them actually, well, at least one of them is not. So at least one of them, you can't actually get back to your original function. Right? But yeah, effectively here, this is what we're trying to do. And I will tell you, this is homogeneous. So this does work. Okay, let me go back now and try and read some of the things because I've fallen behind because I'm just getting pummeled with direct messages. Chen, exactly. Yeah. If you don't have to find the antiderivative, if you can just read what the area is. Agam, what do we do with the u squared? The point is that you don't do anything based off of my conversation here. You want the u squared is going to become the s squared. And it doesn't matter whether you call it u or s, right? Like it's the same thing. If we had a t on the other side of the plus sign, and t, right side, yeah. Here it's kind of really critical that we could sort of like take a t squared out of everything. And if you can't take a t squared out of everything, like you're in trouble, right? Same thing over here. If you tried to show that this function is homogeneous, it wouldn't work. And you'd get stuck and you'd be screwed. Okay, sure. Yeah, Natalia, that's exactly what I want you to do. That's exactly it. And Agam, yes. Though I might have lost our train of conversation. Like you have to still do the substitution, right, Agam? And like you do the substitution, you pull out the t's, but you don't have to do any like more integration or anything like that. Brandon, it depends what you mean by meaningful information. Like, yeah, the t's come out and you get back the original function. So it tells you it's homogeneous, and homogeneous things are important, but like we don't know why they're important. But right, like that's the goal, is to just reduce it back to the original function, but now with more t's. Right, that is what homogeneous. Okay, well, you should pull the t's out, and the t's will come out via your substitution. Right, you're substituting the t's out. So that last part is of order 3. Yeah, this example is an order 3 homogeneous. Agam, you don't have to go back to S because the integral doesn't care what you call that variable. Right? If you want to call it Z or you want to call it happy face, it doesn't care, right? Like if you want to integrate a happy face, D happy face, or SDS or T DT or whatever you want to call it, that it doesn't care about what that variable is called, right? Not DX same, but like DS, but yes. Yeah, Brandon. So, okay, Brandon, look at what we did originally. Okay, look at this example right here. This example, okay? So what did I do? I put the t's in, right? And then I tried to take all the t's out. So you put the t's in, you try to take them all out and just be left with your original function. And this is how you show that a function is homogeneous. Right? So you put the t's in, then you're going to do a substitution so that they come out, and that what you're left over with is just the original function again. Yes, the substitution is effectively what's going to let you pull the t's out. Like try it, you know, so for those of you, hopefully you've now all kind of gotten an idea of what the substitution should be. Try it, right? Go through, you see what the substitution should be, try doing that substitution, see what happens. Like you're not going to be able to do it in your head. You got to be able to write it out. Okay. Depends what you mean, Jeremiah. Like I've set you up here with these two, right? With these things so that you can pull them out. All right. The substitution lets you get them out of the exponent. Right? That's what the substitution is going to win you, is that you can get them out of the exponent that way. Yeah, Jacob. Yeah, that last example at the very bottom of the screen here, that's an order 3 homogeneous. Yeah. And then the upper limit changes. Let's see. Yes, which is what you want, right, Ariana? Because you just want that to be x plus y again. Because the original function just had an x plus y there as well. Okay, so if we sub, yes, yeah, Simon, you have to change the bounds also, but it works out here, right? Yeah, you shouldn't get both multiplied and divided. So Brandon, maybe write it up and throw it on Piazza, and we can we can try and look at it and see what weird things going on there. That no. Long, it sort of depends on like where you're doing that, but generally, because then you could do that for any function, right? It's just multiply and divide, and then every function would be homogeneous. Or it doesn't resemble any shape. What do you mean it doesn't resemble any shape? I mean, they're straight lines, right? So they totally resemble like triangles and stuff. Shania, I'm not certain what you mean. I mean, Shania, if you really want, everything is straight lines. You can just compute the equations of those lines, right? Like if you really want to. You don't have to do that, but you could do that if you really wanted to. Sure. So Davin, what I want you to do is just do it yourself right now. Okay. So you've got this expression. Okay. What I want you to do is let like what if I want to turn this expression into this expression, what should I substitute? Like what should u be? Not S. No, look. Yeah, Kelly, exactly. Okay, everyone. Here's when we plug in the t's, we get this. Yes. Okay. So when we plug in the t's, we get this. I need to transform this back into this function because I'm trying to get it to look like the original function. And yes, this thing has u's instead of s's. but we don't care about that because it's just a dummy variable, like just like when we were doing sums, the integral doesn't care what you call that variable. It's just a dummy variable. So if you integrate the original expression with respect to s, or change all the s's to u's, or change all the u's to w's, it doesn't matter. It doesn't care, right? Exactly. S is a dummy variable, right? Totally a dummy variable. So we don't care. So when I plug in the t's, I get this thing. No, we don't have to integrate it. I plug in the t's, I get this. I'm trying to turn it into a dummy variable. I might call that dummy variable some other name. But if I'm trying to turn u squared, or if I'm trying to turn s divided by t squared into u squared, what should u be equal to? Don't overthink it, right? If I want, Namir, exactly. Brandon, exactly. No, Jack, like you're trying to define u, right? Christian, yeah. So Jack, you get to choose what u should be. And you want whatever u is, this thing, s over t squared, will become u squared. So what should u be? Yeah, great, Cheryl. Yep, same. Yep. Yep. Owen, yep, great. Okay, cool. So, right, for those of you who've got it, this is beautiful. Ooh, not the root log. I mean, Jack, one thing you could do is just literally solve that equation, right? Yes, Jeremiah. Yeah, Long, your answer, like actually, Long, so actually look at your answer, right? You would get s over t squared. That's not quite what you want, right? Because you want s squared over t squared. And then if you square it again, you'd get like s squared over t to the 4. And that's not s over t squared. Right? So actually just look at this equation and solve this equation for you. Right? And that will tell you what the substitution has to be. Yeah, I mean, so showing you in theory that is an arbitrary parallelogram, but you don't have to compute it the exact, but I mean, it's all just triangles, right? Everything there is triangles. So you can just compute it by looking at differences of triangles and stuff. Well, Owen, so you might not be able to see it now, but what I want you to do is carry through the computation and see if it works. And Jack, yes, that's it. Exactly it. Okay, so Owen, carry through the calculation and see if it helps. Long, no roots, right? You don't want any roots because you're still going to square both sides anyway. So don't take any roots. You don't want any roots there. Whoa, where'd the 2 come? Same, like where did that 2 come in? Kayla, yep. Yep, that's exactly it. Yeah, Cheryl, yep. Solve for du and ds, right? And then do your substitution that way. So yes, that would be, yes, that is right. Same, sure. And plug it in. Yeah. Don't forget to change your bounds as well, right? Yes, same. Yeah. And don't forget to change your bounds. So Brandon, you know what substitution to do, right? Because you said it. Like I know you put it in the chat. Okay, just do it. Just do it, see what happens. And if you do the substitution correctly, everything will work out. I don't know what you mean by simplify. I just want you to do that substitution. right? Like your exponent just looks like this thing. So set u to be that, do the substitution, right? Part of the substitution is you got to change the bounds. You got to figure out what du is. You got to figure out what ds is. You know, change your integral, and stuff will work out. What are you trying to do, Chen? I don't quite see it. Then Chen, I think you're undoing. No, but I think you're undoing what I did. Right? Like you got back to here. So I think you're just undoing my work. Yeah, but you don't want that though, right? Like you want your expression to just look like some variable squared. Oh shoot, I erased too much. Okay, you want your expression to look like some variable squared divided by that variable squared plus x squared plus y squared. You don't want any t's to show up anywhere. Long, yeah, beautiful. There it is. Now do your substitution. Okay, so I think most of you have the substitution. I want to move to a different question, but if you know what the substitution is, I want you to substitute. Okay, everything will magically work out if you do the substitution correctly. And remember, t is a constant, right? It's not a variable. T is a constant. Do the substitution, plug everything in, see what happens. It should just magically work. Everything should fall into place. Okay, but just be careful, be methodical, make sure that you do all the things that you're supposed to do in the substitution, and things will work out. Because yeah, some people were asking for some other questions. So I got asked for 9/2, which is not a lot of fun, but sure. So 9-2, let me do maybe just like one of them. So we've got y squared minus 4x equals 3 and 4x minus y is equal to 3. And we want to find the area between these two curves. So if we do that, we've got to figure out, where these two curves intersect and roughly what they look like. So what I'm going to do is I'm going to write this as 4x is equal to 3 minus y. And then I'm going to plug that into here. So I'm going to get y squared minus 3 minus y is equal to 3. So that's y squared plus y minus 3 equals 3. So that's y squared plus y minus 6 equals 0. So that's y plus 3, y minus 2 is equal to 0. So we get y is equal to negative 3 and 2. Okay, so what does y squared minus 4x equals 3 look like? So it's going to be x is equal to y squared minus 3 divided by 4, roughly. So it's going to be a parabola. So here's x, here's y, facing up. And then it's going to peak at negative 3/4, right? So it's going to look something like this. And then the other equation is going to be a line. So it's going to look like roughly like y is equal to 4x minus 3. So it's going to look something like this. And now they intersect at y is equal to 2 and y is equal to negative 3. And you're looking for this area. I would probably integrate this in the y direction. So we're going to have the integral from negative 3 to 2 of the yellow curve if I write this in terms of x, what am I going to get? So I'm going to get 3 minus y over 4. My y's and my 4's look the same. Minus the bottom curve, which written as a function of x is going to be, what do we say, y squared minus 3 divided by 4 dy, and then work out that integral, and there's your answer. So does that make sense? That's like 9-2a. Okay. Christian, were you the one who asked that one, or? Okay, cool. Right, and you don't have to necessarily go through all that work of like figuring out what the thing looks like. You can kind of throw it in Desmos as well. Yeah, no, I mean, long, it will for sure be by tomorrow. It'll probably be like noon tomorrow at latest. Sometimes I do it the night before though. So it sort of depends. It takes a long time for these videos compile, but it'll be it'll definitely be up by about noon tomorrow. Yeah, no problem. Somebody asked about 9-6. So let me do that one. So you've got a box whose vertices are -1, 1. So we've got -1, 1. We've got -1, 0. We've got 1, 0. And we've got 1, 1. All right, so we've got this box here. Let LM be the line with slope M, which passes through the point 2, 0. Okay, so passes through the point 2, 0. Find the value of M, which divides the box into 2 halves with equal area. So we've got some sort of line like this with slope M. And we want to find the slope, which divides the box into 2 halves of equal area. So what's the area of this box? Just by looking at it, what's its width and its height? Not quite. A little too much. I think you went too far. Yeah, you went too far in either direction. Yeah, area is 2, right? So the box has area 2, right? Because it's width 2 and height 1. Is this derivative still S prime and if T is a constant? Simon, yes, but even if S is a dummy variable, its derivative, you have to say, what are you differentiating with respect to? And if you're differentiating with respect to itself, then its derivative is 1. But you're right, the derivative of T is 0 because it's a constant, no matter what you differentiate with respect to. Okay, so what we're looking for is the slope of this, or the equation of this line, such that it splits the area into 2 equal, or such that it splits the box into 2 equal areas. So if the box has area 2, we're trying to split it so that it has area 1, right? Now we can figure out what the equation of this line is, because again, point slope formula, right? So we know it passes through the point 2, 0 and has slope M. So y is equal to mx plus 2, right? Is the slope of this equation. No, sorry, I got those backwards. So it's y minus 0 is equal to m times x minus 2. There we go. So it's m x minus 2. Okay. And so now what we're going to do is we say, okay, we've got to figure out what the how much area it cuts off. And for this part, you kind of have to break it into pieces. So let me break it into cases. So let me draw it. Okay, that's a crappy box. But what we can do is we can figure out where this hits the top of the box. And this part here will just be a rectangle. And then this part here will just be whatever the area under the graph of that thing is, right? So first of all, let's say maybe for what slope is it this? oh man, I can't draw straight lines. What is this slope? So that corresponds to a slope of rise is 1 and the run is 3. So that's negative a third, right? So case 1, M is between negative 1/3. And then if the line is like this and it's outside the box, it certainly doesn't have a chance, right? So if the slope is like that, that corresponds to a slope of what? So rise over run is so -1. Okay, so these values of the slope guarantee that the line hits the top of the box. So in this case, what you would do is you'd say, okay, well, wherever it hits the top of the box, i.e. what we're asking for is when is y equal to 1? So here we find where LM hits the top, i.e. y is equal to 1. So we've got our equation here. We're going to set y is equal to m times x minus 2. We're going to solve that for x. So we're going to get x is equal to what? 1 over m plus 2. I think that looks right. So m, so that's 1 plus 2. Yeah, that looks good. So that's this point right here. So the area, let me just double check what it says. So blah, 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 blah. Find that it divides the box into 2 halves of equal area. Okay. So the area of okay, geez. Yeah, I don't know. Can you guys read that? It says I'm not allowed to stay late because apparently somebody bought me Leafs tickets for my birthday and I have to run. So yeah, so I guess I gotta go. But so this is the deal here. All right, edit. Yeah. So is this okay? Do you kind of see what to do here? Yeah, I don't know. Why would I do that? Yeah, I'm sorry, everyone. I gotta run. Okay. Yeah, so again, just break it. So the first half of that is a rectangle. Second half of the box is just, the area under that line, do the integral and figure it out. Okay, I'm gonna run, everyone. See you later. Ciao.